Welcome. We are discussing GPU computing in the course High Performance Computing for Scientists and Engineers, and we are basically discussing the introductory part on GPGPUs and CUDA. So, in last few classes I have introduced GPGPUs and their architectures and showed what is the difference of the GPU architecture and CPU architecture, and also the programming aspects. And now we are looking into CUDA programming. CUDA is a programming model for GPUs developed by NVIDIA. NVIDIA is one GPU hardware vendor, and we will discuss about the CUDA memory model and threads in the CUDA program in this lecture. So, this is what we have done. We are looking into in our last lecture that how the process flows in CUDA. We understand that we as programmer cannot directly communicate with the GPUs. We cannot ask our programs to directly communicate, talk to the GPUs, directly put the instructions on the GPUs. Whatever programs we are writing, that will be preliminary hosted by a CPU, and CUDA will help us, or CUDA will help the compiler to take part of that job and offload it into the GPUs. Also, the memory of the GPUs are not directly visible to the programmer. So, when he writes the program, he asks CUDA to take a part of the memory, take the relevant memory from the CPU RAM and copy it to the GPU. That CUDA does. Then CUDA asks the GPU threads to be active when a kernel is launched. Kernel is a function which is launched by the main C program. CUDA enables C program here, and that function should be executed in the GPU. So, CUDA asks GPUs to launch threads to execute that kernel, and once this is done, then the output data is written into the device RAM or the RAM of the GPU, and then CUDA copies this data into the CPU RAM, and now CPU RAM data is readable by the programmer. It can be written to the hard disk, or it can be written out to the screen. GPU RAM is not visible by the hard disk or by this by the file systems. So, GPU RAM's data is device RAM's data is computed to the CPU RAM. This is the work process flow in the CUDA. Now, we'll see what we'll see how is the programming model. Any CUDA program is a host plus device application C program. Say it can be C++, it can be Fortran or some other language, Python, Java. So, it is basically a CPU language program with CUDA function calls, and this is integrated with the host part of the program, which will be executed by the host or the CPU, and the device part, which will be executed by the GPUs. The serial or modestly parallel part means it can be parallelized into 4 threads, 8 threads, 20 threads, etc. That runs in the CPU. That is part of the host C code. We are discussing C code here, but it can be in Java, Fortran or some other language. The highly parallel parts, where thousands of threads can concurrently work, that will be following a single program, multiple data kernel code, that will go to the GPU part. That is also like a C program, but it's called as a kernel function, and there are certain syntax in CUDA by which it is this kernel function is identified that this will run in the GPUs, and it is supported for the language like Fortran and C. So, again I'll look into little detail that say this is the first part, this is the serial part which will run in the host or in the CPU. Then the CUDA kernel will be there. The kernel is called like the kernel name, and then the number of blocks and number of threads and the argument. So, when the kernel is launched, multiple threads are launched. I will show you in a while, but these threads are launched as a number of block threads. A block of threads are launched. Inside each block there are certain number of threads, that gives us the total number of threads. And when this kernel function is called, then this massively large number of threads, parallel threads, are launched. And again, once the kernel is over, then the program goes back to the serial mode. In this there is a barrier of the threads, and all the threads converge, and only one thread which is acting only in the CPU that works. Again, if there is another kernel launch, then the program control goes to the GPU, and GPU runs multiple threads there. In between them there are copy host to device. Data is copied from CPU to GPU after the kernel functions are over, then device to host copy. Data is copied, the data that on which the CUDA kernels are working, that data is copied from host to device after the CUDA kernels have done their job, then again it is copied back from device to host. So, in between these copyings are done. These kernels are the functions that are called from the CPU code and executed on the GPU, and kernels return void. GPUs cannot directly return any value to the CPU. Only only the GPU kernels can write, or GPU cores can only write back to the memory device RAM, to the memory of the GPU, and anything which has to be read by the CPU has to be copied using CUDA from the device RAM to the system CPU RAM. So, kernels, the functions that are being called by the main C program and running on the GPUs cannot give any output, cannot write anything back, cannot send any value back to the CPUs. What are they doing? They are only writing in the GPUs. Therefore, kernels should always return void. What are they doing in the kernel? They are updating some memory locations in the device RAM, and this updated memory has to be copied back from the device to CPU. Kernels cannot return anything, kernels will always return void. The output of the kernels will be in the memory of the device RAM. On the CPU RAM, CPU memory, kernels cannot send anything back, and this output will be, which is in the device RAM, will be copied from the device to the host. That is the main part of a CUDA programming model. That first there is a copy from CPU's RAM to the GPU's RAM. GPU does certain work using multiple threads in different blocks, and once the GPU threads work is done, it writes back to the GPU memory, and then CUDA copies the data from the GPU memory to the CPU memory, and now programmer can access that data. GPU memory is not directly accessible to us. We need something like CUDA, which will copy the values from GPU memory to the CPU memory. And then CUDA launches threads in blocks and grids. So, the entire set of threads that is launched by CUDA kernel is called a grid. Inside the grid there are multiple blocks, and inside each block there are number of threads. Why is this so? There is definitely certain reason behind that. We will explore as we will learn it more detail, but two important factors are that scheduling these threads to get the massive parallel thread core architecture of GPU is one factor, and also another factor is that when we are doing writing CUDA program, we are doing scientific computing type of jobs in which we are mostly interested in matrices. So, some mapping with the threads and the matrix rows, that is also important. Each thread ID determines what data to be worked on, and this is a very important part in CUDA programming. We will later learn in detail about thread algebra, that each thread is supposed to work on one particular data, and the threads are mostly relying on registers. They have very small L1 cache and shared memory. So, they are working on small amount of data, but they are operating, they are executing same, each thread is executing essentially same instruction on a specific data location. So, the thread ID should be well mappable to that data location. So, each thread ID will determine which data will be worked on. Now, we can see that when a kernel is launched, it launches a grid, and inside that grid there are multiple blocks. Inside each block there are multiple threads. So when a kernel is launched, it launches thousands of threads, but these threads are not launched as a contiguous set of threads. These threads are launched as parts of different block. Each thread is member of a block, and there are number of blocks, and they follow something like a Cartesian arrangement. We can see here, this is a combination of 3D combination of threads gives us a block here, and a 2D combination of blocks gives us a grid here. So all these blocks combinedly is a grid, and when we launch a kernel, we launch a grid of blocks. Inside these blocks there are multiple threads, so that's how we launch the large number of threads. Threads belong to blocks. Kernel is launched as a grid, which are collection of blocks. So when we launch a kernel, a grid is launched where there are many blocks. Inside each block, inside one particular block, say we took this block 1 1, there are a Cartesian arrangement of threads, and this can be 2D or 3D. The 3 dimension, we can specify how many dimensions, and each thread is therefore identified by the coordinate of the thread inside the block, and each block is identified by its coordinate inside the grid. Therefore, from the block ID, block coordinate and grid coordinate, we can identify the pointer to that thread, and that pointer can be related with the data on which it is operating, and that is called thread algebra. Blocks and grids follow a Cartesian structure. The definition of threads facilitate image processing, because when image processing, it's a pixel based geometry in which the entire display is differentiated into multiple layers and arrangement of pixels on each layer, or matrix computing or array handling, which we will do in scientific computing case. The thread ID inside a particular block is mapped to the matrix data structure in a CUDA program. So we know the thread ID inside the particular block, we know the block ID, combining them we can find a global ID of the thread, which can be mapped to the matrix data structure. Now as threads have multiple coordinates, blocks have multiple coordinates, we can consider matrices of higher dimensions also. This is known as thread algebra. While looking into matrix manipulations, we have to look into thread algebra also. And then it's important to look in the memory architecture of the of a CUDA program. So there is a host CPU which writes data to device RAM. Where it writes data to the device RAM, it writes to the global memory. There are some other memories called constant and texture. Remember, CUDA GPUs have been developed for initially for graphics purpose. So this idea, these terms like texture is there, which are given to the GPU RAMs for the graphics rendering purpose. However, there are two different type of memory, constant and texture. There is another memory on the device RAM which is known as local memory. Now we will see where does these memories exist, and then this device RAM, and device RAM is connected to the main GPU part, the TPCs and multiprocessors, through a bridge interconnect through an interconnect, and inside each multiprocessor there are registers and shared memory. Each multiprocessor, inside multiprocessor we have the computing cores who are accessing registers and shared memories. So in terms of latency, registers and shared memory variables has less latency because they are residing exactly on the multiprocessor. Multiprocessor can very quickly, registers we know that they are on the processor almost, so they can, multiprocessors can very quickly access data from there. But the main global memory as well as what is called local memory is memory associated to each thread, but this does not reside on the multiprocessor, this is on the device RAM. So this has high latency, accessing the local and global memory. The constant and texture, though the name suggests by constant that this value will not be changed throughout the kernel operation. So once the kernel is launched, the constant can be copied to the GPU chip, to the close to the multiprocessors, because we are not changing it, it will be fixed there. And if the multiprocessor, if the cores need to read this value, they can read it from there. So there is a cache for constant and texture which sits on the chip. So if we look into the GPU has two parts, the devices. One is the GPU chip, another is the device RAM attached with that GPU through and with the GPU chip, with the processors or TPCs, texture processing clusters, with an interconnect bridge. Now, if the memory we are considering is on the chip, on the GPU chip, on the TPC, or on the shared memory on the streaming multiprocessor, it can be read very fast, and utilizing that memory gives us better efficiency. So it is important to see which memory is where. The register memory is on the chip. It's not important whether it is cached or not, because it's on the each processor is directly, each core is directly accessing the register. The thread remembers this register. Once the thread is over, the register value it cleans up, it washes up. As the thread is there, it can read that. The local memory is cached. Local memory resides on device RAM. It is cached in L1 and L2, is cached in L1 and L2, and for compute capability 5 it is only cached in L2, but for other devices it is cached in L1 and L2 RAM. So it is a off chip memory, but it is cached to the it is cached in between the device and the in between the RAM and the GPU chip. It is also, the lifetime is also thread. So what a thread is operating on is either the register, the private memory to the thread is the register, or if it requires more memory, it is the local memory. This is private memory, this is not seen to the other threads. This is what we talked about, private memory in OpenMP. Local memory or a register memory is same. Register we know already, it's in CPUs also. Local memory is a part of the private memory. It is residing in the device RAM, so it has a slow access, but it is cached in L1 and L2 RAM. Shared memory, what we talk about, shared memory here is shared by all threads in the block. Shared memory resides in the multiprocessor. So we understand that when we assign a block, all threads in the block goes to one multiprocessor, and shared memory resides, is available to all the threads in the block. There is no requirement of caching this memory, because it is readily available to all the threads there. It's readily available to the chip, so it's very fast, it can be accessed. However, if we need to use L1 cache for some operation, we can assign some part of the shared memory to behave as a cache. That can be done in CUDA programs. The global memory, which resides of the chip, it is for cached in N1 and L2 device by for compute capability 6 and 7, cached only in L2 for other compute capability memories. It is visible to all the threads global memory, as well as it is visible to host. It can be, this global memory can be copied back to the host, and the lifetime is as long as host has copied the memory into the RAM, it will still there. As a host will copy some other memory to that same space, it will change. So this memory is controlled by the CPU only. Constant and texture, they are cached to the GPU chip, but their main location is outside the chip, and they are allocated by host, and they are the read-only memory. The other memories can be read and written by the chips. This is the memory architecture. Yeah. Now we need to keep in mind which memory resides where, and which memory is it where, is how much latent from that. So shared memory and registers can be accessed very quickly by the GPU chips. If it has to access anything local memory, though there is a cache, but it will be slower access, because again this is local memory cache is only for 6 and 7, it is also L2 cache, also L1 cache. Earlier it is L1 L2 cache only, but this can be cached, and L1 caches can be very close to the shared memory, so they can be read quickly. But once it is cached, certain issues related to cache has to be looked into. Whether cache coherency issues will be there, No, because local memory is a private memory, so cache coherence is not there. False sharing is not there because local memory is a private memory. Shared memory is not a private memory, it is visible to all the threads in the block. Therefore, but it's not cached, but therefore the ideas like false sharing type of things might come in the shared memory, though it's not cached, but it is visible to all the threads. And this is read write memory, so all the threads can change this memory. So contentions can happen in the shared memory, and idea of false sharing might come in the shared memory. We have to be cautious while shared memory. However, the shared memory size is small, so when bringing a data from global memory to shared memory, we cannot bring a large amount of data. Only a small amount of data can go and sit in the shared memory. The global memory is accessed by all the threads, and it is also cached, so cache issues might come here. But again, the cache coherency type of protocols, atomic operations are supported by CUDA. Cache coherency protocols are established by CUDA itself. Well, performance on the CUDA and GPU program depends on efficient use of this memory architecture that we understand now. Now, how are the thread and memory architectures in a heterogeneous CUDA program? Why we call it heterogeneous program? Because if we talk about a CUDA, say CUDA C program, it is a program which will not only run in GPU or in CPU, it will run in both CPU and GPU. A part of the program will run in CPU, a part of the program will go to GPU. That's why we call it a heterogeneous program, because there are the simple C instructions will run in CPU and the massively parallel part that will go to GPU. And the execution will be like that initially there will be initially the host will run the serial part, then the kernel will be called, the device will launch the grid of threads, and then all the threads the grid will come as blocks, grid of blocks. Then the blocks will be there, inside blocks there will be threads, so a number of threads will be launched there. Once these threads scopes are over, it will go back to the host, and the host will run another simple C program. Again another set of grid will be launched when next kernel will be called. And when host will ask the device to operate, it will copy the relevant data from host to device, and again once the device's job, the GPU jobs will be done, the relevant data will be copied from device to host if copying is required. Else the data is changed by the GPU device in the GPU RAM only, not on the CPU device, CPU RAM. So if you have to read the changes, you have to copy it from GPU to CPU. In the memory part, when a thread is launched, it operates in the local memory on the register directly, and the thread block operates on the shared memory, and the entire set of threads, they are communicating, or on the grids they are communicating with the global memory. So CPU and GPU have their own memory. Threads first take data from register. If it require more data, the threads operate on a, in the sense threads operate on a private data. They take data from register. If there are more data, they create a local memory and take data from there. The blocks can use the on chip shared memory, then you have to ask the blocks to operate on that memory, and the entire set of grid, they are using the memory which is residing in the device RAM. They are connected to the device RAM's data. And CPU to GPU memory transfer can be only done by copying, allowing CUDA to copy data from CPU to GPU or vice versa. Also, lately CUDA has come up with unified memory programming architecture. Unified memory eliminates the requirement of copying data from CPU to GPU and GPU to CPU, rather makes the memory visible to all CPUs and GPU. So it some way connects the gives a virtual sense of connected memory in between the CPU and GPU. GPUs of class Kepler and above with CUDA version 6.0 plus or compute capability or SM architecture 3.0 plus facilitate unified memory programming. Programming becomes simple here because it is the same set of memory which both CPU and GPU is visualizing. Instead of looking into different memory and copying, unifying memory space with coherency across all CPUs and GPUs are seen here, and it gives a more tighter association of CPUs and GPUs and more straightforward implementation, because you really do not need to think about copying back and copying out here. And the data access is maximized by migrating data towards the processor using it. So, data will reside in one particular location in the CPU RAM. If the CPUs are working, then it is visible to the CPUs. If the GPUs are working, the data will be migrated to the GPU RAM, and that support is provided by the newer architecture of GPUs, which are started from CUDA class Kepler SM architecture 3.0 plus, and the newer version of CUDA compatible to that CUDA version 6.0 plus. So, this gives more flexibility to the programmers, as I told you earlier that GPUs are evolving in terms of flexibility and performance. So, this gives more flexibility to the programmers, and the performance tuning is also better possible here. However, we will stick to the legacy version of CUDA programming, that is a non-unified memory or programming approach, or a heterogeneous memory approach, where we will consider GPU memory and CPU memory separately in our programs, because we are specifically interested here in seeing how different elements of GPU memory are connected and how we can operate over on chip and off chip memory efficiently to get right performance. The one serious extremely important advantage of a unified memory program is that if there are multiple GPUs, as we can see here, the performance, the multi-GPU programming is facilitated much easily in unified memory architecture. So, we will some point of time try to discuss some aspects of multi-GPU programming, and then we will see the effects of unified memory approach. But now, while learning CUDA program, we will stick to the heterogeneous memory approach and look into CUDA mem copies between device to host and host to device, considering them as separate memory entities. Well, so we looked at, one of our reference is Shane Cook's Developer's Guide to Parallel Computing with GPU. NVIDIA has number of releases, documents and presentations on GPU and CUDA. Because we are looking into CUDA programming, which is proprietary of NVIDIA, I am heavily relying on materials provided by NVIDIA, and two of the important reference manual are CUDA programming guide from NVIDIA and white paper on Volta or V100 architecture. These two we have consulted heavily, and it is important for any CUDA program developer that you go through CUDA C program guide if you want to learn CUDA programming, or if you have learned CUDA programming, if you want to optimize your applications, you must go to the CUDA programming guide. If you are a Fortran programmer, there is, we will discuss it in next class, there is a similar Fortran CUDA Fortran guide, which is provided by both NVIDIA and PGI, which gives the Fortran compilers. Well, so the conclusion is we have discussed GPU architecture and programming modules, introduced CUDA while discussing GPU programming model, and the memory and thread hierarchy in CUDA and GPU program presented. In next class, we will look into CUDA detail and we will start looking inside the CUDA programs. Thank you.